The topic that I'm going to talk about today is predicting canopy cover, a view from above. I'm Danny Su, and I'm going to introduce the method of remote sensing and how we can use remote sensing to understand canopy cover. Scientists are very interested in canopy cover. It can tell us a lot of things from different types of tree, how they're growing in different types of ecosystems, to even how trees are distributed in different elevations, how they are surviving after fire, or even what kind of animals living in the tree, how they're utilizing different cover of the tree, and what kind of animals is suitable for what kind of canopy environment. Additionally, it can also help us understand what are some of the forces that's destroying the forests. For example, in Brazil, there are cows and deforestation that's associated with cow raising. All these studies can be known if we can know about canopy cover. So far, there are technologies that help us measure canopy cover. For example, one can take a camera and then face it upward on the canopy, and then using a computational model, one can calculate the percentage of canopy cover, which is a method called hemispherical image. One can also use something called LiDAR, which stands for light detection and ranging. With LiDAR, there are several ways. There are terrestrial LiDAR, which one uses it like a big camera, or as you can see, there are these LiDARs that are being carried either by unmanned vehicles or by an airplane. And with these, they actually help us understand, with LiDAR in particular, it shoots off these laser and it hits on the surface and returns. And when it returns, it actually gives us readings at each height. So with LiDAR, we can get all these different types of tree modeling that can tell us how high the tree are, and also what are the branches at different, what are the leaves density at different heights. And these dots, like for example, the more dense the dots are, the more dense the leaves are. But these technologies actually are limited in terms of scale. It can tell us maybe a few hectares of canopy cover, but then in order to understand how the earth is changing, we need something that's at a more macroscopic scale. With different types of satellites, they record at different waveband, and each waveband reveal a different characteristic about the vegetations. For example, Sentinel-1, this type of satellite mostly receives SAR data. It has it's good for estimating water body. And then for pulsar, it also sends out these microwaves that actually is really good for estimating biomass. And for Landsat, it has several different type of waveband, and one of it is visible light that's widely used to map images such as that seen in Google Map. And today I'm going to talk specifically about a case where they use satellite data to produce a global canopy height model. And this global canopy height model can then be used to produce canopy cover model. In the paper produced by Long et al., they merged two types of satellite data. One is the Sentinel-2 data, and another one is the LiDAR data from the JEDI mission. And with the Sentinel-2 data, they compile it with the geocoordinates, and then using the canopy height estimate from the JEDI, they then run a supervised machine learning through the convolution neural network, and then classify each Sentinel-2 image, and then finding the corresponding height. And at the same time, they also estimate the variance of such an estimation. And with this method, they were able to produce a global canopy height model. And then, in order to evaluate the accuracy of such global canopy height map, they then held out 20% of their training data for testing, and then 80% then go to training. And they found out that at different Jedi reference heights, there are different residuals, which is, in this case, the difference between the estimate and the Jedi reference height, which they held as the ground truth. And they also compared the estimations at different ecosystems. For example, in mangrove, deserts, forests, tundra, etc., etc. And with these, they found out that there are different residuals associated with different ecosystems, meaning that this model performs differently in different types of ecosystems. Thirdly, they then compared the accuracy with the previous model by Potapov et al. 2021, in which they also use LiDAR data from Jedi and merge it with Landsat data to produce canopy height model. And they found out that overall, their prediction is more accurate than Potapov as compared, as evaluated with the reference Jedi height. And then they compared this with more fine scale, more spatially fine LiDAR estimate of canopy height at different independent sites. And with these, they are able to compare with Potapov and found out that they actually produce a better model. With uncertainty, they actually discussed two types of uncertainties. One is aleatoric uncertainty, which is the essential noises associated with satellite detection. And so in order to address them, one, they actually produce the variance within each machine learning model to understand how each model estimate that variance. Another is they actually try to compile multiple sentinel pixels from multiple dates on the same pixel. So then they can then compare how the prediction varies. And then they also talk about the epistemic uncertainty, which is trying to understand how these models perform differently. And this is something that they can control. So what they did is they trained 5 machine learning models and then compare how they differ among themselves. So with these, knowing the accuracy and uncertainty, we then have to ask, given that no model is perfect, and as scientists, we do want to know as best as we can about the ecosystem. However, with the given accuracy and uncertainty, sometimes we have to find a middle ground. So here I want to give an example. Imagine there's a lion on the landscape, and as an ecologist, I want to understand how the lion is utilizing the landscape based on the canopy cover. So for me, if I define canopy cover as something that a tree is taller than 2 meters, even if my bias of my prediction might be 1.8 meters, if I get an estimate of, let's say, 4 meters, it doesn't really matter for my prediction model. And also, with the uncertainty that's associated with these predictions, sometimes in ecology, there is a certain range of certain range of estimate that might equally be ecologically significant. And that, for example, 20% canopy cover might have a similar effect on lions as 30% canopy cover, or they might not care about canopy cover at all. So depends on the type of ecological question that I'm asking. Different types of accuracy and uncertainty are needed in the study.